Alright, day 2. We're going to continue on 14.4. We're going to continue looking at parametric equations, and we're also going to look at derivatives now using parametrics. So we want to further understand parametric equations and understand calculus applications to parametric equations. So first, let's look at the parametric equations x equals cosine t, y equals sine t. I want you to think about, or actually I want you to figure out, what does this set of parametric equation represent? Where does it start when t is 0? And what direction does it go? So pause the video, think about and answer those questions, unpause when you're ready to check your work. Okay, so if we start to plug in points, specifically if I plug in t is 0, x is 1, and y is 0. So I know I start at the point 1, 0. Now, if I look at these equations, what are they saying? Well, the first one is saying x is cosine, y is sine. That is what we say for the unit circle. So if you continued to plug in points for t and plot them, you would see that your shape is a circle. Specifically, it's going to be the unit circle. We're very excited. That's the exclamation points. And the direction is then going to be counterclockwise because that is the direction of the unit circle, starting at the point 1, 0. So this is what our graph would look like if we were to actually graph it and plot out specific points. But for this, we don't need to because we hopefully could have recognized that if x is cosine and y is sine, that gives us the unit circle. Next, what would the parametric equations be if we were to start at 0, 1 instead of 1, 0, but still go counterclockwise? And then also, what would the parametric equations be if we were to start at 0, 1, but go clockwise? So I want you to think about and try to answer these two questions. Pause the video, come up with parametric equations, unpause when you're ready to check your work. Now in this case, there could be multiple correct answers, so keep that in mind. Alright, so one example of starting at 0, 1 and continuing counterclockwise would be if x equals negative sine of t and y equals cosine of t. You could also say x equals sine of negative t, y equals cosine of t. You could say x equals sine of negative t, y equals cosine of negative t. That would work as well. Going clockwise, we could have x equals sine of t, y equals cosine of t. That would start at 0, 1 and go clockwise. Okay, so some helpful tools for plotting points. This is what we're going to get to next, although we're not going to do a ton of plotting here, but this is stuff we want to think about. One is just noting the direction the path takes. So we need to kind of be aware by plugging in a few values to see which direction the path is going to go. And then how could we use calculus? Well, we can use calculus just like we do with graphing polynomial functions or any other regular functions, and that is we can find maximums and minimums or changes in direction using the same techniques that we do for regular functions by finding the derivative and the critical values and the second derivative and possible points of inflection. So now getting to derivatives, if we have the parametric equations x equals t squared plus 1 and y equals 2t when t is between negative 5 and 5, I want you to find dx dt, dy dt, and then dy dx in terms of t. So pause the video and find each of those derivatives. Unpause when you're ready to check your work. Okay, so if we want to find dx dt, dx dt is going to be 2t because we're going to take the derivative of the x and t relationship with respect to t. If we want to find dy dt, we're going to take the derivative of the y and t relationship with respect to t, so that's going to be 2. And if we want to find dy dx, well, I know dy dx is dy dt over dx dt. So if I take 2 and I divide it by 2t, I get 1 over t. Now, I could also find dy dx by first substituting in to the x or the y equation for t. So for example, if y equals 2t, then I know t equals y over 2. So I substitute y over 2 into the x equation. So I get x equals y over 2 quantity squared plus 2. So x equals y squared over 4 plus 1. I'm sorry, I said plus 2 up here, plus 1. Now when I take the derivative with respect to x, remember, the derivative of x is 1. The derivative of y squared over 4 is going to be y over 2 dy dx, and the derivative of 1 is 0. So now if I rewrite this to solve for dy dx is 2 over y, but remember, y is 2t, and I want the derivative dy dx in terms of t. So then I can substitute in for y, 2t, so I get 2 over 2t, which is 1 over t. So either method works. Either getting the parametric equations in terms of a rectangular equation and then doing dy dx, or recognizing that dy dx is actually dy dt over dx dt. Okay, so now using these equations and these derivatives, here are some things I want you to think about and figure out. Where are the maximums and minimums for each variable? Over what interval is x decreasing? And which intervals is x increasing? Over what interval is y decreasing? And over what intervals is y increasing? And I want you to justify all this with calculus. So pause the video and unpause when you're ready to check all of your answers. Okay, so first I did the x value. So I know dx dt is 2t, so if I set that equal to 0, I get a critical value of t equals 0 for the x's. So then I made an increasing decreasing chart, or you could do your second derivative test. And I plugged in -1 and I plugged in +1. I saw that it changed from negative to positive. So since x prime of t is less than 0 on -5 to 0, and x prime of t is greater than 0 on 0 to 5 at x equals 1 is a relative min for x. And then I did absolutes as well, so because we had a closed interval, when x is -5 and when x is +5, I'm sorry, when t is -5 or when t is +5, x is 26, so that is going to be an absolute max for the x values. And when t is 0, x is 1, which is an absolute min for the x values. It's also a relative min. So those are the x values. Dy dt was 2. Therefore, there is no relative min or max. It's increasing the entire time. But we can do absolute mins and maxes. So when t is -5, y is -10, so that is an absolute min. When t is +5, y is 10, so that is an absolute max for the y values. So doing all that work gives us our increasing and decreasing intervals. So x is decreasing from -5 to 0 when t is -5 to 0. Since x prime of t is less than 0, on -5 to 0, and x is increasing when t is 0 to 5, since x prime of t is greater than 0 on 0 to 5. Over what interval is y decreasing and increasing? Since y prime of t is greater than 0 on the interval -5 to 5, it's increasing the entire time. Okay, so now I want you to think about what you could do in the last example to reverse the path, reverse the direction of the path. So I want you to pause the video, think about this, unpause when you're ready to check your work. Okay, so I think the easiest way to reverse the path without changing the entire set of parametric equations is to make it x equals t squared plus 1 and y equals -2t. Okay, so then just kind of summing up parametric equations again, how do they help? Well, they help us if we use parametric equations for a curve that is not given by a function. So for example, if I have x equals 8 theta minus 4 sine theta and y equals 8 minus 4 cosine theta. That's going to be hard to write as a function. Actually, it's going to be impossible. We can use parametric equations to describe paths. Each coordinate requires one function, and the parameter may be time, angle, or something else altogether. So in conclusion, we know how to convert parametric equations to rectangular and back and forth. Don't forget to check the domain. That didn't come up in our problems today, but we want to keep that in mind. And also now we have seen how calculus can still apply by finding maximums and minimums for the specific variables in the parametric equation. Also, I would like to give a shout out to 2nd, 7th, and 8th grade classes. Almost there. Just keep doing what you're doing.